All right, so now we're going to look at this idea of continuously compounded interest. So we've already discussed the idea that compound interest is the most common kind, and continuously compounded is the most common of all of the compound interest kinds. So continuously compound is the idea that the bank is constantly giving you money. So we start with our compound interest formula, but now we're going to let our n be our interest rate times x. So we're compounding this continuously. We want to put an x in there so we can find the limit as x goes to infinity. So if we think about this, we're going to end up dividing by a number so big because we're compounding constantly, like every second, that this part of it is going to end up getting reduced lower and lower to so low that our r's eventually are going to cancel out. So let's let our n equal rx. So if we substitute that in, we get b equals p times 1 plus r over rx raised to the n, we're changing out with rx, t. If I simplify these, I see that my r's cancel. So I'm going to have a 1 in the numerator. So b is equal to principal times 1 plus 1 over x raised to the r x t. And now it says use the power to a power rule. So I've got a power, all of these are multiplied. That's the same as a power to a power. I want to rewrite it with my RT left out. So my RT is left out. So that means this I'm going to take in and write as a power to a power. So on the inside, I'll have 1 plus 1 over x raised to the power x, because I know a power to a power is just multiplied. So these things are equal. All right, so now if we let x become infinity, what happens to the inside? So let's look at the limit as x goes to infinity of 1 plus 1 over x to the x power. And maybe you remember what this is, but maybe you don't. So let's go look at our calculator. So I've already typed this in, 1 plus 1 over x to the x, and I'm going to look at the table of values. So I'm going to go into my table settings. I'm going to start at 0 and go up by 5s. All right, so then I'm going to, and that's just because I want to see sort of what happens as time goes on. So into my table settings, 0 I get an error because of course I can't divide by 0. But now as I go up, I notice my number is getting bigger and bigger. So that's at 50. Let's go into our table settings and let's start at 50 and let's start going up by 10s and see what happens. And we're getting closer and closer to 2.71. Remember what 2.71 is? Hopefully you remember that that is our friend, the natural number, not pi. The natural number is here. And we see 2.71, which is what this limit becomes. So that means my continuously compounded interest formula becomes principal times e to the RT, which we saw in our logs and exponents unit, and now we see where it comes from. So here's our compound interest formula. And we're going to go back to answer to examples 6 and 7 and change to continuously compounded interest. So let's look at example 6. That was our one where we had these values to start with. So I'm going to copy this and paste it down here. Paste it somewhere. Where did it go to? Let's try that again. Well, doesn't go anywhere. So we had 15,000 as our principal. We had an interest rate of 4.25%, and our total number of years was 5. So rate was 4.25%, and our total number of years was 5. So continuously compounded would tell me that my balance would be 15,000 times e to the 0.0425 t. Sorry, my t is 5. So remember, our calculator has that handy e to a power button. So 15,000 times e to the power of 0.0425 times 5. And we get our value ends up being $18,000, just over $18,000. So we don't have the 50 cents, we don't have $52 yet. We have $18,550, $551. So I'll leave you to redo example 7, and you can look at the notes to see when it's completed.